Okay, so I will go through the assignments 1 to 4. The first assignment is on introduction to electrochemistry, also introduction to EAS. The second assignment is on instrumentation, on selection of single sign or multi sign and the implications. The third assignment is on data validation using Kramer-Kronig transform, and the last one, fourth assignment, is on equivalent circuit analysis. So, in the first assignment, the first question is what is the relationship between electrochemical rate constant and potential, and the answer I was expecting is exponential. You can write exponential, you can write exp. Some of you have written exponentially, which is all right. Okay. What I want you to note is that rate constant will vary exponentially with potential, but the current may not go exponentially. Okay. If I draw current versus potential, I do not expect that it will always be like this. In fact, in majority of the cases, it is not going to be exponentially varying, it might increase and then saturate. It is not going to be linear, but current in general will not be exponentially varying with potential. Only in special cases it will vary exponentially with potential. The next question is, in the 3 electrode cell, it is preferable to have a large area counter electrode. Is it true or false? And of course, you want to have a large area counter electrode. Large meaning compared to the area of working electrode, the area of the counter electrode should be large, because in a 3 electrode system you have working electrode, you have reference electrode and you have counter electrode. The potential is measured between the reference and the working, but the current passes between working and counter. So, this potential between the reference electrode and the counter electrode has to be adjusted, so that all the current passing from working electrode goes to the counter electrode. And if you have large area, it will put less load on the potentiostat. The next question is, in the capacitor, when you apply sinusoidal potential, you wait for some time, you will get steady periodic response for current. In that case, what is the phase difference between the current and the potential? Okay. The current leads the potential or lags the potential. When we say it leads, if this is potential versus time, when I draw current, if it is in synchronization, we will say phase difference is 0. If it goes like this, we will say it leads. If it looks like it is starting later, of course, when I say it looks like, I mean it is achieved steady periodic result, and then it looks like it is starting later, we will say it lags. Okay. In case of capacitor, the relationship between current and potential is given by this equation, that is derivative of potential with respect to time, multiply that by capacitance, you would get the current. And when we apply sinusoidal wave, we would say E as ES is 0 sin omega t. When we take the derivative, we will get omega ES is 0 cos omega t, and when it is cosine, we can write that as sin omega t plus pi by 2, which means if this is potential, we are going to see a curve which leads the potential by pi by 2 radians or 90 degree. The next question, if j is square root of minus 1 and a sinusoidal potential of angular frequency omega is applied, okay, the impedance of an inductor, that is given by j omega L. Answer C is the correct choice. You can also relate the potential and current using a similar differential equation. You can calculate the impedance by using this formula j omega L. And similar question, when omega is the angular frequency, if I take a capacitor and I want to find the admittance admittance is denoted by y, and that is inverse of impedance, and that is going to be j omega c, because the impedance is 1 by j omega c. Therefore, the admittance is going to be just j omega c. C is the correct choice. The next question, you have to consider 3 resistors. We can arrange them in parallel, we can arrange them in series. Okay, one is 50 ohms, another is 30 ohms, another is 10 ohms. If you arrange them in series, you have to add these resistance values to get the total resistance, that is 50 plus 30 plus 10. So, you should get 90 ohms when they are arranged in series. When they are arranged in parallel, you have to add the admittance of each of these element to get the total admittance. That means 1 by 50 plus 1 by 10 plus 1 by 30 would give us the total admittance, and if I take inverse of that, it will give us the total impedance. So, that value is going to be 6.5. So, if you write somewhere between 6.4 to 6.6, you should get the full credit. Of course, this is similar to what you have seen before. It is just testing whether you can remember the relationship between current and potential for a capacitor, and that has to be current is dE by dt multiplied by capacitance. The next question is, if you connect a capacitor in series with a resistor C and R, okay, the overall potential between these two terminals, we call that as E. Part of the potential drop occurs across this capacitor, we can call that as EC. A part occurs across the resistor, call it as ER. Current passes through this system. Now, what is the relationship between the current and the capacitance and the resistance and the potential drop across these elements? Okay. Now, the total potential drop is EC plus ER, and that is going to be the total potential that we apply. The current through the capacitor is going to be the same as the current through the resistor. So, we can write IC equal to IR. The relationship between potential across a resistor and the current is R equal to ER by IR. Because IC equal to IR, we can just call that as I. Therefore, I can write I equal to ER by R. I can also write that as E minus EC by R, because ER is E minus EC. Now, the relationship between current and the capacitance. So, now we have an equation which relates the potential drop across the capacitance to the capacitance value, potential and the resistance value. It is a first order differential equation. You can solve it provided you are given the correct initial conditions. Right now, all that I want you to recognize is that the relationship that describes this circuit is given by the choice D. So, in the next question, you are given a circuit, you are given values. Our solution is given as 20 ohms, charge transfer resistance is given as 150 ohms, and double layer capacitance is given as 20 microfarads, and at a particular frequency 100 hertz, we want to find the impedance and write the real part and the imaginary part. So, we have this circuit, the impedance of this entire circuit can be written as R solution plus the impedance of the resistance and capacitance in parallel, okay, and that is going to be given by 1 by RT plus j omega C dl. The terms within the parenthesis or brackets tell you the admittance of this resistor and capacitor, and inverse of that gives you the impedance of this system. So, if you substitute for these values, omega is of course 2 pi f, you should get the real part to be close to 53 and the imaginary part to be close to minus 62. And the next question is, in this circuit, if I calculate the impedance or if I estimate the impedance at a frequency of 0, what would be the value, and at infinite frequency what would be the value. Okay. At 0 frequency, what happens is no current passes through this capacitor. So, you essentially have two resistors in series, one at 20 ohm and another at 150. So, you should get 170 ohms when the frequency is at the limit of 0. When the frequency is very high, capacitor offers very little impedance. So, all the current will go through the capacitor and no current will go through this resistor in parallel. So, that net resistance is only 20 ohms. Next, in the instrumentation, what is the lowest frequency one can employ in most commercial instruments? Is this something that you have to remember or look up? You can get instruments that can measure impedance at a frequency of 10 microhertz. Okay. It is going to take very long time to do, but this is what is claimed by the instrument manufacturers and this is something available to you. The next question is, for batteries, what is the common mode of measuring EAS? Okay. Normally, we measure in pseudo galvanostatic mode or pseudo potential static mode. For batteries, fuel cells, for batteries and fuel cells, energy devices, it is normally done in pseudo galvanostatic mode. So, that is option C. And in general, kinetics manifest in low frequency or high frequency or mid frequencies. Okay. Kinetics usually manifest in the mid and low frequencies. At high frequencies, most of the current passes through the double layer capacitor. So, we will not have any significant impact on the kinetics. B is the correct choice here. Next question is, where will we get higher harmonics? Okay. If a system is linear and if you use multi-sign, you should get only response at fundamental. So, you will not get higher harmonics. If you apply a DC bias, you will not get higher harmonics. Only if the system is non-linear, you can expect higher harmonics. Okay. So, the answer is choice A. If the system is non-linear, you can get higher harmonics. The next question is Taylor series expansion of e power a sin theta. Okay. There are different ways of looking at it. You can say I want to look at Taylor series expansion in terms of theta. You can also say I want to look at Taylor series expansion in terms of sin theta, sin square theta, etc. So, if you look at the choices provided, first choice writes in terms of theta, but that is actually e power a theta, that is the expansion of e power a theta. Okay. Second choice of course is not at all suitable for this. The third choice takes this expression e power a sin theta and expands this as 1 plus x square by 2 factorial. So, instead of x you use a sin theta. So, third choice is the right one. Now, if the signal frequency is expected to be 3 hertz, then to acquire 5 cycles, how long should you acquire the data? Okay. Frequency is 3 hertz. That means the time period is 1 by 3 second. Okay. If I need to take 5 cycles, 1, 2, 3, 4, 5, the number of cycles is in the numerator, the time period is in the denominator. So, you get 1.666, anywhere between 1.6 and 1.7 you would get credit. Next, in the FFT analysis, the number of harmonics that we can measure, okay, it increases. What I mean is, if you get a time domain signal, but it is discrete set of data points, right. You transform that to Fourier domain, you would get response at fundamental 2f, 3f, etc., up to a finite harmonic. You can get phase, you can get magnitude. Okay. So, if I want to get more number of harmonics, what should I do? Should I increase the time of measurement? Should I sample at a faster rate? Okay. Should I make it shorter? Should I sample less? The answer is, of course, you have to sample at a faster rate. Okay. If you increase the duration, what happens is the resolution in the frequency domains become more, that is, instead of 0 f to f, you can get 0.1 f, 0.2 f, etc. Okay. So, the duration in the time domain, that is related to the resolution in the frequency domain, and sampling rate, if it increases, then the number of harmonics that you can get increases. The next question, you have multi-sine wave that is created by combining two sine waves. Okay. One sine wave has a frequency of 1.25 hertz. Okay. Another sine wave has a frequency of 2 hertz. If I combine these two, what is the period of the combined sine wave, multi-sine wave? Okay. So, what you have to do is to find how long you have to combine them, so that you can get a unit that is repeatable. Okay. In this case, the combined wave has a frequency of 4 seconds. Okay. It comprises of a wave at 1.25 hertz, okay, 5 cycles of that, and 8 cycles of the second wave. Okay. 5 cycles of first wave and 8 cycles of second wave gives you one wave. So, the period of oscillation for the first wave is actually 1 by 1.25 seconds, right, that is little less than a second, and the period of oscillation for the second wave is half a second, but the combined wave has a period of 4 seconds. Next, consider two sine waves. Okay. One has a frequency of 1 hertz, the second wave has a frequency of 2 hertz. Now, if I multiply these two waves and integrate it from 0 to some value, some of the integrals will go to 0, some of them do not go to 0. So, you are supposed to identify which one goes to 0. If you look at the first integral, it goes from 0 to 1, the period of the first wave is 1, period of the second wave is actually half. This is f1 sine wave of f1, sine wave of f2. When you multiply, these are orthogonal, and you go from 0 to 1 period, this will go to 0. The first and second wave are the same waves. Okay. So, when you multiply, this will give rise to a non-zero value. The first wave and second wave are different. However, the integral does not go from 0 to a period or n periods. It goes from 0 to 1.8, which means this integral will not go to 0. The fourth one goes from 0 to 2, which is actually like 0 to 1, except that it is twice that period. F1 and F2, they are orthogonal, therefore this goes to 0. The second one, it is not orthogonal, they are parallel to each other. F1 and F1 are parallel to each other, therefore it does not go to 0. So, the choices B and C are non-zero. So, here choose all the correct options to improve the signal to noise ratio, basically to get a good quality data. You can do the following. You can increase the amplitude of the potential if you are applying pseudo potential static mode. Okay. You can average for many number of cycles, average for longer time, that will also improve the signal to noise ratio. Okay. Of course, when you increase the input amplitude, there is a danger, there is a possibility that you might go into nonlinear regime. As long as you are in the linear regime, increasing the amplitude helps. If you go to nonlinear regime, you will still get a clear signal to noise ratio, but your spectrum Only thing is you can't interpret it assuming that the response was linear. Third assignment. EAS data is acquired from following system. It consists of resistor and capacitors. It was validated using KKT by integration. So, I am just describing a scenario to you. The original data and the transformed data do not match well. What could be the reason? One choice is, was a large amplitude perturbation used? Did we use 100 millivolts potential? Should we transform it in the admittance mode? Maybe we transform in the impedance mode, therefore, it was coming wrongly. Or did we transform in the admittance mode, whereas it should have been transformed in the impedance mode? Or the last one, which is frequency range was limited. Okay. This is a circuit. Inherently, this is a linear system. This is a simple circuit with resistors and capacitors. Therefore, it is a linear system. This does not have any active elements. It is automatically KKT compliant. Whether you use large amplitude perturbation or small amplitude perturbation, it does not matter. Likewise, whether you use admittance mode or impedance mode, it should not matter. Only possibility is that the data was not taken in a wide enough frequency range. So, that is the only reason why data was not KKT compliant. If one of the conditions of linearity, stability or causality is violated, can we guarantee that the KKT will flag that? Can we guarantee that the KKT will flag that violation? The answer is no. Okay. If a system was linear, causal, stable and you take spectrum from that, it would be KKT compliant. But even if it is not linear, sometimes the spectrum will be KKT compliant. So, basically these are sufficient conditions, but these are not necessary conditions. Although our experience is, in general, if there is a violation of stability, KKT will detect that. Violation of linearity, sometimes KKT detects it and sometimes it does not detect it. And what do KKT equations relate? They can relate the Z real and Z imaginary. They can relate mod and absolute value and the phase value. We have equivalent relationship in the admittance, real and imaginary, or phase and magnitude. Okay. So, choice A is all right, choice B is all right. They do not relate impedance and admittance, of course. Okay. And it is pretty much the same question asked in a different way. KKT is known to be sensitive to violations of stability. Okay. Sometimes it is sensitive to the violation of linearity and sometimes we know that it will not detect the violation of linearity. And impedance spectrum from a circuit consisting of only passive elements, okay, that is always KKT compliant. Whether you apply multi-sign, whether you apply a small amplitude or large amplitude, whether you apply a single sign or multi-sign, the spectrum that comes out of that should be KKT compliant, as long as you acquire the spectrum in a wide enough range and test for KKT compliance. Okay, we know that if there is a potential instability, it is quite likely that KKT test will flag it. Where do we expect to see the difference? Okay. The effect manifests mainly in the low frequencies. Even in the spectrum, if you are able to take a spectrum without instability and with instability, usually the difference between the spectra arises or shows up mainly in the low frequencies. Okay. So, here this is the choice B. If the real part of an impedance spectrum has negative values, means if I draw a complex plane plot minus Z imaginary versus Z real, may go like this. The real part of the impedance has negative values. then this spectrum can be converted to a spectrum like this if we take this system and add a large enough capacitor in series, that is one choice, add a large enough resistor in parallel, second choice, small enough resistor in series or small enough resistor in parallel. So, if you add a small enough resistor in parallel, this is likely to go to the right side. The reason is at low frequencies, this is going to give you a resistance. This resistance plus this net impedance, when they are in parallel, this is going to give you a resistance, and you should add the admittance of the Z on the top and the admittance of this resistor. If it is a small value, then the admittance will be a large value, and the total admittance is going to be dominated by the large admittance value. So, this has to be a small resistor. Next, if we take measurement model approach for spectrum validation using KKT or equivalent approach, then what circuit should you use? Maxwell, White or ladder? You can actually use any one of these. Okay. They are all equivalent. So, if it fits well with Maxwell, it should fit well with White, it should fit well with ladder. So, any one of A, B, C is okay. Now, if the impedance spectrum is acquired at 3 frequencies per decade. So, if I draw it in a Bode plot, I will just make up this mod Z and minus phi as a function of frequencies log scale. If it is sparsely populated, there are very few points here, then what approach should I take for data validation? Okay. Can I take a measurement model approach? Can I use linear KKT software? Can I use the integration in the impedance mode, and can I use the integration in admittance mode? I can take measurement model approach, I can take linear KKT software, which is basically measurement model approach with some constraints. I should not use direct integration of KKT in either in impedance or in admittance mode, because I am going to approximate these segments by straight lines, and that is not a good approximation. Okay. Here the question is, which technique will not be suitable? So, the answer is C and D are not suitable. And next is an ES data shown as complex plane plot, goes to the right, takes a loop and then comes back and settles at the negative side. This is taken from a stable system, okay, and the perturbation amplitude was small. So, we know that it is linear and stable. Okay. We expect that spectrum to be KKT compliant. However, when you validate with KKT, we find that there is a difference. The transform data is shown by the red color dashed line, and the original data is shown here. It looks like a mirror image. When you see this signature, what conclusion should you draw? Is it because, well, you know the answer, right? This has to be transformed in the admittance mode, and if somebody has transformed this in the impedance mode, they would see what looks like a mirror image in the low and mid frequencies, and it will be compliant or it will match well in the high frequencies. So, choices that are given to you are, is it because it is acquired in a limited frequency range, or is it because you have used direct integration by KKT, or is it because data was transformed in the impedance mode? The reason is, it is because the data was transformed in the impedance mode. If you use direct integration, and use the transformation in the admittance mode, this would work well. The original data and the transformed data will match well. The fourth assignment. So, you have a complex plane plot of impedance spectrum shown here. It looks like a semicircle. You are given 4 choices. Out of these, which model should you use or at least start with? Okay. If it is an electrochemical system, I would normally start with this option B. The reason is, I expect to have certain solution resistance, I expect to have certain double layer capacitance, and there might be a reaction. Now, all these 4 circuits will model this equally well, okay. But it is easy for me to interpret the choice B. Okay. I can model this with choice A or C or D with perhaps negative values for this inductor values and corresponding resistances, but getting a physical meaning out of that is going to be difficult. So, B is the correct choice here. The next question is, if you are given the Nyquist plot or complex plane plot of a spectrum which looks like this, you have one arc here, second arc followed by the third arc. Okay. Which circuit should I use? Choice A, B, C or D. If you look at this spectrum, I can say there is one time constant for the first arc, second time constant, third time constant. I need a circuit with 3 time constants, this RC, second RC and third RC. So, this is the suitable circuit. I have an inductive loop, which means one of these pairs will have to have negative values, that is all right, but I cannot use this circuit, I cannot use the second circuit, I cannot use the fourth circuit. It has an inductor that can model this part, but the remaining 2 parts cannot be modeled. Okay. So, you need to have 3 time constants and C is the correct choice. You are given a system where R3, C3 and R4 are given. R3 is 1000 ohm, C3 is 100 microfarad, R4 is 250 ohm. If I want to get an equivalent circuit with a different configuration, a resistor in series with a system where you have a capacitor in parallel with resistor R6, what are the values of R5, R6 and C6? Okay. So, you can actually find the relationship between these 2 circuits, relate R5, R6 and C6 to R3, C3 and R4. It is easy to find the relationship between the resistances. With little more work, you can find the relationship between the capacitor or inductor as given here. Okay. You can also use the software that is available in our website, but that is more like you can get the answer, but without knowing how it came. Okay. If you look here, at 0 frequency, no current passes through this. At 0 frequency, no current passes through this. So, I can say at 0 frequency, on the left hand side that impedance is going to be R4, on the right hand side the impedance is going to be R5 plus R6. So, I have a relationship saying R4 equal to R5 plus R6. At infinite frequency, all the current will pass through this and no current will pass through this. So, net impedance is R5. At infinite frequency, current will pass through R3 and R4 in parallel. So, I will say R3 plus R4, the net impedance of that is, you take the R3 inverse plus R4 inverse, that will give you net admittance, take the inverse of it, you will get net impedance, that should be matched with R5. So, you can essentially get the same relationship. I am just rewritten the equation. So, you have one equation relating R5 and R6 to the R3 and R4. You have another equation, 2 equations, 2 unknowns, you can rearrange them and solve. You get one equation R5, another equation for R6 in terms of the elements on the left hand circuit. You can also write the impedance of this entire circuit and the impedance of this entire circuit and equate them. Okay. Since you already know the relationship between R5 and R6 with R3 and R4, you had to solve this, rearrange and get the relationship between C6 and all the components here, and you will find that you get C6 is related to C3, R3 and R4. Once you substitute in these equations, you can get the equivalent values, and they are going to be 200 ohms, this is going to be 200 ohms, this is going to be 50 ohms and this is going to be 0.0025 farad. Similarly, you are given another circuit and you are asked to find what are the corresponding resistance values and the inductance value. Similar to what we had done in the previous case, you can write the 0 frequency impedance of the left hand circuit and you can write the infinite frequency or high frequency limit of the right hand circuit and left hand circuit. So, 0 frequency, this will give you R4, 0 frequency, this will give you R7. So, these two R4 and R7 are directly related. R3 and R8, you have to actually combine, it is not directly related. R8 is a function of R4 and R3. Okay. There are different ways of writing it, this is one representation. And of course, once you know these two, you can write the impedance of the left hand circuit and the right hand circuit and come up with this relation, which says L8 is going to be related to C3 and R4. Using these values, you can show that this is 250 ohms, this is minus 50 and this is minus 6.25 Henry. Because you are moving from a capacitor based circuit to inductor based circuit, some of the values are going to be negative, but the impedance that you get out of this throughout the frequency range, they will be identical. Okay. Next question is, we have a impedance spectrum which looks like this. You have a high frequency capacitor and a low frequency inductor loop. I want to use the circuit on the right hand side to model this spectrum. What should I do, especially in terms of choice of these element values? Okay. If R3 is negative, can I model this? If C3 is negative, can I model this? If R2 is negative, can I model this? The answer is, if R3 is negative and C3 is negative, when both of them are negative, you can match the inductive loop. Okay. If only one of them is negative, you will not be able to match the inductive loop. Next question, you have a spectrum which looks like this, you have inductive loop followed by a capacitive loop, but it goes to the negative side. If I want to model this, I should allow this value to be negative, I should allow one of these R4 C4 can be negative or R3 C3 can be negative. Any one of this pair, if that pair is negative, I can model the inductive loop, and if R2 is negative, I can model the low frequency negative resistance. Okay. So, it has to be A and B, okay. That means the answer is C, because you are given both of the above, or only R2 is negative or only this combination is negative. You are given a spectrum and you are asked to find the charge transfer resistance and polarization resistance. Okay. Of course, you have to look at it visually and say this probably would reach 40 ohms. If this was extended, this is where it will hit. So, somewhere close to 40 ohms is where it will hit here, and close to 90 ohms is where it ends, but then solution resistance is close to 10 ohms. So, 30 ohms is charge transfer resistance and 80 ohms is polarization resistance. Next, you are given this circuit and you are told that this circuit is able to match a spectrum generated by a electrochemical system. This represents solution resistance, this represents double layer capacitor. Can you estimate the charge transfer resistance and polarization resistance? Here in this circuit, the remaining terms here, remaining elements here represent the Faraday impedance. If I apply a zero frequency sine wave or close to the zero frequency, a sine wave of low frequency, no current will pass through this, no current will pass through this capacitor, which means 1000 ohm is going to be the polarization resistance. That is the exact value. If I apply infinite frequency sine wave, if I apply very large frequency sine wave, then this gives 0 impedance, this gives 0 impedance. Current will pass through a network which has 1000 ohm, 250 ohms and minus 500 ohms. And you can calculate the admittance of each one of these, add them up, you will get the net admittance. You can take the inverse of that, that will give you the net impedance, and that is close to 333 ohms, and that is going to be the charge transfer resistance. Similarly, you are given a different circuit. The previous one was Maxwell circuit, this one is ladder circuit, you can think of it as a void circuit. Here if I apply 0 frequency, no current will go through this, all the current will go through this. So, the sum of these two resistances 25 and 35, 60 ohm is going to be the net impedance at the limit of 0 frequency. If I give very high frequency, all the current will go through this and it offers no impedance or negligible impedance. So, 25 ohm is the charge transfer resistance.